Hello everyone. Our next problem is 562. Problem is like this. The two shafts are made of A36 steel. Each has a diameter of 25 millimeters. We will modify the problem. So we will use 50 millimeters for the diameter. And they are supported by bearings at A, B and C, which allow free rotation. If the support at D is fixed, determine the angle of twist of end A when the torques are applied to the assembly as shown. Okay, so we have a system with two shafts, and at point D, the second shaft is fixed to a ball. Then we have a 120 Newton meters of torque applied to the shaft. Which is far away from, which has a distance of 250 millimeters from point D. Then we have the bearing C. It allows free rotation. Then we have the gear. Identically, we have the second shaft from A to B. The bearings A and bearings at A and B allows free rotation, so there is no resistance coming from these bearings. Then there is a torque applied to the gear, which is 60 Newton meters, as is shown in the figure. And finally, this torque is transmitted to the second shaft with this two gears, which has a radius of 100 millimeters and has a radius of 150 millimeters. Okay, so now first thing is to draw the free body diagram of the system. In fact, we don't know the support reaction at point D, and we don't know the torques transmitted through this gear system. Therefore, let's begin from the shaft AB and draw the free body diagram of it. Indeed, it has to be in static equilibrium. Okay. So let's begin by drawing the free body diagram of the shaft AB. This is my shaft. This is my point A. Then I have my point B here. That's okay. So next, we have the moment, which is 300 millimeters away from the point A, and this moment is towards the right hand side according to the right hand rule. I will call this moment as M1. Certainly this system has to be in static equilibrium, therefore the moment torque on the gear has to be in the opposite direction, and I will say that this is mg1. So this will be my first gear, and obviously because of the static equilibrium I can easily say that mg1 is equal to m1, because sum of the moments has to be equal to 0. Remember that M1 is equal to 60 Newton meters, therefore mg1 is equal to 60 Newton meters. Now, of course, now I need to calculate the moment transmitted to the second shaft. Now let's draw the shafts, gears, in fact, 2 gears. Now let's assume that I look at the system from B to A. Therefore, I have my small gear and I have my large gear here. Okay. So in my small gear, the direction of the rotation is clockwise. As a result, this moment has to be generated by such a force. A force which is in this direction. So because basically when you have a 2 coupled gear, the force is transmitted by the gears, and certainly the big gear applies a force to the small one in this direction. Now, since action equal to reaction, the reaction force has to be in the opposite direction on the big gear. Now this is, let's say, Fr. Therefore, magnitudes of these forces has to be equal. Now this small gear has a radius of R1 and the big one with R2. Now this will generate a moment in this direction. So again, a clockwise direction. Now let's write the force. Fr is equal to mg1 divided by R1, and that's equal to mg2 divided by R2. Now R2 is equal to 150 millimeters, so 0.15 meters, and R1 is equal to 0.1 meters. Now from here I know the mg1, therefore I can calculate the mg2. mg2 is equal to R2 divided by R1 multiplied by mg1. If you put the values, R2 is equal to 0.15, R1 is equal to 0.1, and mg1 is equal to 60. So this is my torque on the second gear, so the big gear. So this is 3 divided by 2, this makes 90 Newton meters. Now let me draw the free body diagram of the second shaft, which is fixed to the wall. So this is my shaft. This is my point D. I have my point C here. Now, certainly I have my externally applied torque between D and C. It has a magnitude of 120 Newton meters. So M2 is equal to 120 Newton meters. Then I have the torque coming from the gear at the free end. This is mg2, which is again 90 Newton meters. Now let us draw the well, certainly I have the torque at D. I forgot it. Let's say that this is MD. Now I can calculate the MD easily. Certainly I choose an arbitrary direction, so I don't know the direction of the MD. So MD is equal to, in fact, M2 minus mg2, because sum of the moments has to be equal to 0. This is 120 minus 90, which makes 30 Newton meters. Now let us draw the free body diagram of the shafts. Sorry, not the free body diagram of the shafts, I apologize. Torque distribution. So basically I will make cuts, and I will begin from the first shaft. So the shaft AB. First I will cut the structure between A and moment 1. This is what I'm going to do. This will be the first thing that I'm going to do. This is my point A. Remember that I always take the direction of the torque, internal torque, always normal to the cut and towards the outside of the piece that I've cut. So I will say that this is T1. Certainly sum of the moments has to be equal to 0. As a result, T1 is equal to 0. Then I will make a second cut. Now I have my torque M1. This is T2. Therefore T2 is equal to minus M1, which is minus 60 Newton meters. Then I will make the third cut between the gear 1. So between the gear 1 and point B. Which results in this. So this is M1, this is mg1. I have my third internal torque, so T3 is equal to mg1 minus M1, and that's equal to 0. Now I have my torques. I can draw the diagram for the first shaft. This is my point A. This is my point B. This is where my torque is applied, M1, and this is where my gear is. So, and this is minus 60 Newton meters. As you see, we have only torque between the moment 1 and gear 1, else it is 0. Okay, so let's do the same for the second shaft. I just draw the free body diagram once more. So this is my MD, this is my M2, and then I have the mg2. Okay, now I know all the values. In fact, I can begin to cut the structure from any point, so it doesn't matter. I will begin to cut the structure from point D for simplicity, so I will make the first cut from here. This is MD, sorry. This is T1. In order to differ it from the first shaft, I will put a prime on T1. So T1 prime is equal to MD. And remember that the value for the MD is 30 Newton meters. Now I will make a second cut. Between the moment M2 and the gear. So this is T2 prime, this is M2, and this is MD. In fact, T2 prime is then MD minus M2. So this is 30 minus 120, which makes minus 90 Newton meters. Oh, sorry, I made a mistake here. Oh, sorry, it's okay. Yeah, it's minus 90 Newton meters. So now we have the distribution. Let's draw the torque distribution for the shaft. So first I will begin from D. So this is my point D. In fact, between D and first torque I have a constant torque, which is 30 Newton meters. Then I have negative 1, which is minus 90 Newton meters. So this is the torque distribution for the second shaft. Okay, now I have the torque distribution. Now next I need to calculate the angle of twist. In fact, first thing that I need to do is to calculate the angle of twist of gear 2 with respect to the point D. This is what I'm going to do. Okay. Now first I'm going to calculate the angle of twist of the shaft which is fixed to the wall. So angle of twist for the gear 2. Remember that I have two different regions. And now let us define some variables first, maybe. So first okay, so I will define this 250 millimeter distance as L1. L1 is 0.25 meters. Then I have my second distance. So from the torque, which has a magnitude of 120 Newton meters, to the gear 2, the distance is 750 millimeters. So 0.75 meters. Now I have my second distance from B to the third distance from B to the gear 1, which is 300 millimeters my fourth distance is 250 millimeters. And L5 will be from the 60 Newton meters of torque to the bearing A, which is 0.2 meters. So these are my distances. Okay. So next, now these are my distances. You see L1 is 0.25 meters, L2 is 0.75 meters, and it goes like this. Fine. Now I will calculate the twist, angle of twist for gear 2. So the gear 2 is, the angle of twist is, first angle of twist generated by T1 prime, L1 divided by rotational moment of inertia multiplied by the shear modulus. This is the first relative twist of the location where the torque is applied, then plus T2 prime L2 divided by J rotational moment of inertia multiplied by the shear modulus. Now we need the shear modulus value, in fact, and rotational moment of inertia. So shear modulus for the steel is 75 gigapascals. This will be given to you. Rotational moment of inertia is equal to P r to the power 4 divided by 2. So remember that radius is 25 millimeters. We modified the problem. So instead of taking diameter 25 millimeters, we take the diameter as 50 millimeters. If you put this value, so this is 25 10 to the power minus 3 divided by 2, so the value that we are going to have is 6.13 multiplied by 10 to the power minus 7 meter to the power 4. Now I have all the values. Let us put the values into their places. So T1 prime is 30 Newton meters. This is 30 multiplied by L1. L1 is equal to 0.25 divided by J. J is 6.13 10 to the power minus 7 multiplied by 75 10 to the power 9 plus T2. Now T2 is negative, minus 90 multiplied by 0.75 divided by 6.13 10 to the power minus 7 multiplied by 75 10 to the power 9. Okay, this is our relative angle of twist. If you do the calculation, what you are going to get is 1.3 10 to the power minus 3, of course this is minus, radians. This is the relative deformation, relative twist of gear 2. Now, we always assume that the deformations are small. So as you see, we have a very small rotation. Therefore, what will be the rotation or generated by this twist? What will be the rotation in gear 1? Now, just return back to our problem. Now we have two gears. One big and one small. And we know that small one has a radius of R1 and the large one has a radius of R2. Now, since the deformations are small, in fact, these two gears will make the same amount of rotation, not the angle, be careful, same amount of rotation. So therefore, the point on gear 1 will make the same amount of displacement with the point on the gear 1. So at the point of contact, they will make the same amount of displacement. So this is phi G2 and this is the angle of rotation of gear 1. Since the deformations are small, I can easily write that R1 multiplied by phi G1, the rotation of gear 1, is equal to R2 multiplied by rotation of the, or the angle of twist of the gear 2. Okay, so this is how I'm going to find the angle of twist of gear 2. But there is one thing that we have to be careful. So remember that gear 2 is rotating in this direction. And since as a result, in fact, we know that the gear 1 is rotating in this direction. Okay, so when it goes from displacement from here to here, it makes a displacement from here to there as well. So okay, so from here I can calculate the rotation angle of twist of gear 1. So the gear 1 makes a rotation R2 divided by R1 multiplied by twist of gear 2. So I know all the values. You can put the values, in fact. So R2 is equal to 0.15, R1 is equal to 0.1, and this is equal to minus 1.3, 10 to the power minus 3, which gives me a value of minus 1.95, 10 to the power minus 3. Okay. Now this is my angle of twist at gear 2. Now I need to calculate the angle of twist of point A with respect to gear 1. Now, as we know from the torque distribution, we have only torque between the applied moment and the gear. So I don't have any torque between point B and gear and point A to the applied moment. Therefore, I only need to calculate the angle of twist for this part. So, angle of twist of A with respect to the gear is equal to T2 multiplied by L4 divided by J multiplied by shear modulus. Now the value for the T2, the torque, is minus 60. L4 is equal to 0.25. Rotational moment of inertia is 6.13, 10 to the power minus 7. And shear modulus is 75, 10 to the power 9. Now, if you do the calculation, what you are going to get is minus 0.32, 10 to the power minus 3 radians. In fact, the total angle of twist of point A is equal to rotation of A, angle of twist of A with respect to the gear, plus angle of twist of gear 1, which is minus 0.32, 10 to the power minus 3, minus 1.95, 10 to the power minus 3, which makes minus 2.27, 10 to the power minus 3 radians. So it is result for our problem.
Hello everyone. Our next problem is 577. Let's read the question. First, the steel shaft has a diameter of 40 millimeters and is fixed at its ends A and B. If it is subjected to the couple, determine the maximum shear stress in regions AC and CB of the shaft. Shear modulus of the steel is given as 75 gigapascals. Okay, so we have a steel shaft fixed at both ends. We have a force couple. The magnitude of the force is given as 3 kilonewtons, and the distance between the two forces are 100 millimeters, and its position is given. So the load arm has a 600 millimeters is 600 millimeters far away from point B and 400 millimeters far away from point A. Okay, so in fact, as we see from the figure, this problem is hyperstatic, or in other words, statically indeterminate. We cannot calculate the reaction forces at support A and B by using the methods that we have in statics. So, but there is something that we can easily say. If you look at the problem, the relative twist of angle of twist of point B with respect to A is 0, or relative twist of A with respect to B is 0. And this is one thing that we can use. In fact, for this purpose, first we need to draw the moment distribution. So let's begin by drawing the free body diagram of the problem. This is the first step that we are going to do. Okay. Sorry for the delay. Okay. Right. Now, let's define the variables first. We have the radius R is equal to 20 millimeters. Now we will define some variables. First of all, sorry for the delay. Okay, so we have this 400 millimeters distance. We will call it LA. LA is equal to 0.4 meters. Okay, then we have this distance 600 millimeters. We will call it LV. Okay, then we have the distance of the force to the axis of rotation, so this 50 millimeters distance, we will call it D. Okay, now we have the force F. F is equal to 3 kilonewtons. Now we can so these are my variables. Now we can draw the free body diagram of the system. So let's draw the free body diagram of the system. This is my shaft. This is my point A. This is my point C. C is somewhere here. Okay. Now I don't know the direction of MA and MB. Certainly I can choose any direction for MA and MB. In fact, again I will choose MA towards the left hand side. This is the reaction moment or torque at point A. Then I have the reaction moment at point B. In fact, this force couple will generate torque in counterclockwise direction if I look at the system from point B. Therefore, it is in this direction. Okay, so this is my free body diagram. Now, first thing that I'm going to do is I will write static equilibrium for this configuration. So MC plus MB minus MA is equal to 0 from static equilibrium. Now there is another quantity. I need to calculate the rotational moment of inertia, J. So remember that R is 20 millimeters. I will do it here. J is equal to P R to the power 4 divided by 2. So this is P 0.02 to the power 4 divided by 2. If I do the calculation, the value that I will get is 2.51 10 to the power minus 7 meter to the power 4. Okay. Now I need to draw the torque distribution. In fact, I can begin to cut the structure from any side, either from the left hand side or from the right hand side. In fact, I prefer to choose I will first cut the structure from between A and C. Let's say that this is T1. And then I have MA here. So T1 is equal to MA that's okay. Now next I will cut the structure between C and B. This is MA. This is MC. And this is T2. So T2 is equal to MA minus MC, and this is equal to MB. It's okay. So now we know the torques in region 1 and region 2, therefore I can write the angle of twist from A to B or B to A, doesn't matter. So I will write angle of twist of B with respect to A. So, and I know that relative twist is 0, and this is equal to T1 LA divided by J multiplied by G plus T2 multiplied by LB divided by J multiplied by G. Okay. So from here I can easily write that MA multiplied by LA plus MB multiplied by LB is equal to 0, and in fact I can say that MA is equal to minus MB multiplied by LB divided by LA. Or I can write MB as well. So MB is equal to LA divided by LB multiplied by MA. So these are my two equations. Now I can substitute, I can choose either MB or MA as the dependent variable and can substitute into one. So I prefer to, sorry, this is minus by the way. I prefer to write MB by means of MA, and will substitute into equation 1. Therefore from equation 1 I will have MC minus LA divided by LB multiplied by MA minus MA, and this is equal to 0, and from here I can find MA. So MA is equal to MC divided by 1 plus LA divided by LB. So this is my expression for MC. Now I know the value of MC. I can easily calculate it. In fact, MC is equal to force multiplied by D divided by 1 plus LA divided by LB. If I put the values, so force is 3 multiplied by 10 to the power 3. D, by the way, this is 2D, okay, 0.1 divided by 1 plus LA is 0.4 and LV is 0.6. From here what I obtain is 180 Newton meters. So this is my torque. Okay, so now I'm going to calculate MB. MB is equal to minus MA multiplied by LA divided by MB, LB, sorry, and this makes minus 120 Newton meters. Now I need to calculate it has asked me the value of the maximum shear stress. I know that maximum shear stress occurs at the surface of the shaft, and in fact I have two torques. One is 120 Newton meters and the other one is 180 Newton meters. In fact, if I draw the torque distribution along the shaft, this is what I'm going to obtain. I leave it to you how to find it. You can easily find it. So this is my point C, and then I will have a degrees down to point B. So this point is minus 120 Newton meters, and this is 180 Newton meters, and this is my torque. So certainly if I look at the torque distribution, obviously I will see the maximum shear stress at a point where my torque is maximum, since the radius is constant. Therefore I can easily say that I will see the maximum shear between A and C. Tau is equal to MA multiplied by R divided by J. MA is equal to 180. Radius is 0.02 divided by J. J is 2.51 multiplied by 10 to the power minus 7, and the value that you are going to have is 14.32 megapascals. This is the answer of the question. Okay, thank you very much. This is maximum. Let's solve the problem 581. Question is like this: the shaft is made of A36 steel and is fixed at end D, while end A is allowed to rotate 0.005 radians when the torque is applied. Determine the torsional reactions at these supports. Okay, so we have a rod fixed between two walls, but the support at A is allowed to rotate either in clockwise or in counterclockwise direction with an angle of 0.005 radians, 5 10 to the power minus 3 radians in fact. We have two torques applied to this shaft. One is 55 kilonewton meters and the other one is 28 kilonewton meters. Diameter of the shaft is given as 150 millimeters. The distances are given. From A to B is 450 millimeters. From B to C is 600 millimeters, and from C to D is 450 millimeters. Okay, so first thing that we need to do is to draw the free body diagram of the system. So this is what we are going to do next. This is my shaft. This is my point A. Then we have our point B here, point C here, and D is the other end. Now we are given the directions of the torques. So the torque is, if you look at the shaft from point D to A, the the torque at point B is in this direction. In other direction. So according to the right hand rule, we use the right hand rule, and at point C it is towards the B according to the right hand rule. In fact, we can choose the torques at point D and A, the direction of the torques at point D and A arbitrarily. So I choose both of them from left to right. So this is MA, this is MB, this is MC, and I have MD. In fact, I don't know the values of MA and MD. I have two unknowns and I have only one equation. Therefore, I cannot solve the problem just by using static equilibrium. I need an additional equation, and that comes from the rotation of the shaft. In fact, the maximum twist of point A with respect to D is given. It is 510 to the power minus 3 radians. In order to write the equation for the twist, first I need to draw the torque distribution. This is what I need to do. Okay, I can begin to cut the structure either from point A or from point D. I prefer to put my origin to point D, and I will cut the structure beginning from point D. So first I'm going to cut between D and C. And let's say that this is torque 1, this is MD, therefore torque 1 is equal to MD. Next I will cut it from B and C. This is my X, by the way. This is my torque 2. This is my MC. This is my MD. So torque 2 is equal to MC plus MD. Okay, so next step, I will cut the structure from B and P. So let's draw it here. This is my MD. This is my MC, then this is my MB, this is my torque 3. Torque 3 is equal to MC plus MD plus MD minus MB. So this is my torque, these are my torques. In fact, I can write the relative angle of twist for each region now. But first I need to or let me write the formula directly, it doesn't matter. So my angle of rotation, let's say I calculated PDA, that's equal to T1 multiplied by length of point D to C divided by rotational moment of inertia of the shaft multiplied by the G plus T2 LCB divided by J multiplied by G plus T3 LBA, and that is J multiplied by G. Okay, so I know T1, T2 and T3. In fact, from here I can put the values into its places. So J multiplied by G multiplied by VDA is equal to T1 is equal to MD, MD multiplied by LDC, plus T2 is equal to MC plus MD multiplied by LCB plus T3 is equal to MC plus MD minus MB multiplied by LBA. Rearranging the equation gives us MD multiplied by LDC plus LCB plus LBA plus MC multiplied by LCB plus LBA minus MB LBA. Now if I look at the equation, look at this equation, the only unknown that I have is MB. So MD here in this equation. From here I can easily calculate the MD. So MD is equal to J multiplied by G multiplied by PdA minus MC LCB plus LBA plus MB LBA divided by LDC plus LCB plus LVA. Okay. If you put the values into their places, what you are going to get is 11,656.6 Newton meters for the reaction moment at point D. Now, from the moment equilibrium, I can easily say that MA is equal to plus MB minus MC minus MD. If you put the values into their places, what you're going to get for MA is 15,343.4 Newton meters. Please check the values again. Check the derivation. Okay, now we will continue with the thin mold cross sections. So how to calculate the maximum shear in case of a torsion in a thin mold structure. The maximum shear on a thin mold structure can be calculated as bending the torque applied, MB, okay, divided by 2 multiplied by the average area multiplied by the minimum thickness of the membrane. So rotational moment of inertia can be calculated as 4 times square of the area divided by sum of the U average divided by delta. So delta is the thickness of that part. In fact, the angle of twist can be calculated as torque applied MB multiplied by the length divided by shear modulus multiplied by the rotational moment of inertia IB. Here we denote the rotational moment of inertia here as IB, and UAB is the average circumference. We will see it much more better. We will understand it much more better when we solve the problems. Okay, our first problem is 5.114. Determine the torque T that can be applied to the rectangular tube if the average shear stress is not to exceed 84 megapascals. Neglect the stress concentrations at the corners. The mean dimensions of the tube are shown, and tube has a thickness of 3 millimeters. Okay, so we have the mean dimensions. It has a height of 100 millimeters and thickness width of 50 millimeters. We apply a torque. First, we are going to calculate the average area. Average area is circumference multiplied by the thickness. Thickness is shown by the delta, and it is given as 3 millimeters. So 0.02 times 0.05 plus 0.1 multiplied by 3 10 to the power minus 3. From here we can find the average area as 9 10 to the power minus 4 meter square. Okay, so rotational moment of inertia is equal to 4 times square of the average area divided by circumference divided by the thickness. So it is 4 times 9 10 to the power minus 4 square divided by 2, 0.15, it is 1, multiplied by 2, it is the average circumference, divided by 3 10 to the power minus 3. So from here you can find the rotational moment of inertia as 3.24 10 to the power minus 8 meter to the power 4. Okay, so we are given the allowable shear stress. Allowable shear stress is given as 84 megapascals, and that has to be equal to the applied torque divided by 2 average multiplied by the average area multiplied by the thickness. From here I can calculate the applied torque or moment, and that is equal to T allowable multiplied by 2 times the average area multiplied by the thickness of the profile. If I put the values, the allowable shear stress is 84 10 to the power 6 pascals multiplied by 2. Area is 9 10 to the power minus 4. The thickness is 3 10 to the power minus 3, and from here I can find the maximum torque as 151.2 Newton